It'll mostly just be writing and stuff anyways, then it'll be great. All right, so I guess we'll start off with any questions from the last video? No, everybody's okay? Doing all right with all the rocket stuff?
Yeah.
Sounded good. All right. Okay. Still no Rebecca. Yeah. Let's see here. Put more people on. There we go. The last two people. Okay. So, yeah. So let's pick up. So today we're going to finish this chapter, and then I'm going to have you guys work together for a little bit. So that'll be fun. And then yeah, so then next time on Friday, I guess we'll start the next or the next chapter. So we might get done a little early today. We'll see how that works. So, but anyways, if nobody has any questions, last thing we're going to talk about is the center of mass. Center of mass. So cool. So let's say I have an object. So here's my object. Beautiful. And I want to know the center of mass of this object. And let's say it's located here. So the center of mass. So one thing I'll point out is the center of mass of an object is uniquely defined by the object. So this is uniquely defined by the object itself. The object. Now, what we're going to do is we're going to come up with a vector that describes the location of the center of mass. So basically, all that means is we have to choose some sort of coordinate system. So here's my coordinate system. So let's say that's X and Y. And then we're going to come up with the center of mass position vector. So we'll call that my position of the center of mass. Now, first thing to note is even though the center of mass is uniquely defined, the location of the center of mass according to that coordinate system will be coordinate system dependent. So this guy here is coordinate system dependent. So the location of it is going to depend on the coordinate system that I choose. So different coordinate systems will have different locations, but again, that location on the object itself will be always the same because it depends on the actual object itself. So, how do we determine the location of the center of mass? Well, the way we would actually determine this is we would use torque, but in this case, we're going to just write down the answer to this. So let's say I have a collection of objects. So let's say here's, I don't know, mass one here, here's mass two here, here's mass three. So we're going to do this for discrete first. So mass four and etc. So each one of these guys then is going to have a vector which points to its location. So it's position vector. So R1, R2 here, R3, and etc. So R4 is the last one. So in this case, we define the location of the center of mass, capital R, as then being equal to the weighted sum of the mass of the object times the position of the object, divided then by the total mass, which we're going to write as capital M. So this is simply a weighted average. So this is a weighted average. Yeah, weighted average, which basically weights the location by its mass. So I know we talked about this in 205 before, but all this says is that the more massive it is, the more important it is. Important it is. So good. So all this says is my center of mass of my system may be sitting about here. So my center of mass position vector is going to point at this location, for example. So again, the more massive it is, the bigger the mass that this guy has, then the more it's important to the location of the center of mass. So again, the more massive it is, such as myself, in this case, would be more important than, say, my water bottle here or this pen or etc. So if I'm trying to find the center of mass of these things, it'd be closer to me because I am gigantic. Okay, cool. So since this is in Cartesian coordinates, this means that in Cartesian coordinates, I never spell Cartesian right. But anyways, in Cartesian coordinates, we can split this up into component form. So components So that means that we can find the center of mass location in the x direction. So I'm going to write that as x. So this is 1 over the total mass, which then is the sum.
Hey, can I interrupt for a second?
You absolutely can.
Can you let in my other device? I think it's in the waiting room.
Oh, yeah, sorry. I'm too busy looking at my iPad. So, okay, you should be in. Cool. So the mass times its x location. So this is the x location. The y location then would be 1 over the total mass times the sum over the weighted average of the y positions. And then finally, in 3 dimensions, this would be 1 over the total mass. The weighted average then of the mass times its z location, where my total mass, of course, is just equal to the sum over all the masses. So this is the discrete version. So again, all it says then is what? If I have discrete objects, then we would just find the location of each one of those objects in that particular coordinate system, weight it by the mass, and then simply sum them all together and divide by the total mass. That's it. Nice and easy. Okay. Now, if I have a continuous object, so it's like a continuous objects. So for continuous object, let's go back to that original drawing that I did here. So in this case, again, let's choose our coordinate system. So here's my coordinate system. So x and y, for example. So here, to determine our center of mass location, we would chop this thing up into a whole bunch of basically discrete objects. So here's my different discrete objects. So cool. So let's call this one delta M1, delta M2, delta M3. That's not a delta, that's a box. Delta M3, and etc. Each one of these guys then has their own position vector. So this is going to be R1, R2, and R3, and etc. And then that's going to have some sort of center of mass position here. So there's my center of mass position. So cool. So as we know from 205, our center of mass position, again, is going to be equal to, or what we just did, is 1 over the total mass, the sum then over all of the individual masses, which in this case I'm going to call delta mi, times the position vector at which it's located, which is ri. Now, from here, we're then going to take the limit, since it's a continuous object, as delta mi goes to 0 of 1 over the total mass, the sum over I of delta mi ri vector. But what's the limit of a sum?
Integral?
An integral. So this is going to be the same thing then as 1 over the total mass integral of the position vector weighted by the differential mass. Is okay? Look familiar, I hope. So good. So last thing is dm has no physical meaning to it, as we talked about in 205. So usually what we do is we turn this differential mass into a geometrical integral. So that means we're going to write this as either lambda dl if I have a line symmetry to it. I'm going to write it as a sigma dA if it has a volume, or sorry, an area symmetry to it. Or I'm going to write it as a rho dV if it has a volume symmetry. It's early in the morning. I can't talk today. It's okay. Let me make that look like an actual dV. There we go. So for those of you who have not had me in the past, I usually write my volumes this way with the unibrow on top. So that's to distinguish it from things like velocity. So I'd write my velocity this way. And for example, if we do magnetic, then I would write my potentials this way. So just that way, when you're looking at your notes, you know which one it is that you're actually talking about. So we know each one of these guys. So one thing to point out, just like we had pointed out in 205, is that these guys here don't need to be constants. So these don't need to be constant. They can be position dependent. So, for example, I may have a profile of the linear mass density of an object which increases as I move away, for example. So, so cool. So that's center of mass. That's pretty much about it. Now, again, I can split this up into Cartesian coordinates if I want to, which basically means that we're just going to look at the x portion, the y portion, and the z portion. And then the only other thing I should put here that I forgot to put is now the total mass becomes the integral over dm. Unlike in this discrete case where we would simply sum all these guys together. So again, in Cartesian coordinates, we would again just split this guy out. So let's write it that way. So in Cartesian coordinates for the continuous, so this is 1 over my total mass, integral of the x position integrated over the mass. For the y, this is now going to be 1 over the total mass, integral of the y position integrated over the differential mass. So again, my weighted average. And my z is 1 over m integral z dm. So again, these are all just simply weighted averages. Averages. And again, depending on what type of symmetry I'm going to have, I'm going to use my different dm's depending on my symmetry. So let's do a couple examples of this. Let's see how this works. So first one we're going to look at is a hemisphere. So let's say I'm looking at, I don't know, the top part. So here's my northern hemisphere. And I want to know what is the center of mass for this solid hemisphere. And let's say that this guy has a continuous mass density, or a constant mass density, I should say. So continuous mass distribution. So my rho in this case is simply equal to a constant. So cool. Now, before we move on, let's go ahead and find our constant mass density. So what we know is that mass density, in this case, is equal to the total mass divided then by the, in this case, volume. So this is going to have the total mass. So whatever mass this guy has. So let's write that as just total mass. And let's say this thing has a radius of A. So this thing has a constant radius of A. So what is the volume then of a hemisphere?
2/3 pi a cubed.
Right, so 2/3, because it's half of that of a sphere of A cubed. Good, so I'm going to move the 3 to the top. So it's going to become 3 times the mass divided by twice pi A squared, or sorry, cubed. So this is my mass density. So next things next is we can choose our coordinate system. So again, we can choose whatever coordinate system I want to use to make my life easier, i.e. we want to use the symmetry of the problem to our advantage. So for example, to find the location of the center of mass of my hemisphere, would I want to use this particular coordinate system? For example. Probably not, right? Because again, I have to do some sort of integral. So I have to do a rho dm in this case, which means that what? Trying to do the integral based off of this coordinate system would suck. This is not something you'd want to do, right? So what's the best coordinate system that I should choose in this particular case? Where should I put my coordinate system? Or where should I put the, what's that?
Like spherical coordinates or that?
Well, let's say Cartesian coordinates. And where would I want to put my origin specifically?
At the center.
At the center, right? So let's call this my x-axis. Let's call this my y-axis. And then let's call this my z-axis. Cool, cool, cool. So Brayden, I think you answered that question. Why do I want to put it at the center? If I put it at the center, what's going to be true about both the x and y location of the center of mass?
Um, it'll just be on the origin.
On the origin, right? Which means that automatically by choosing this coordinate system, I know both the location of the x and y center of mass location will simply be 0, which means the only place it's going to be non-zero is in the z direction. So it's going to be somewhere around here-ish, right? So this is going to be my overall center of mass location. So it's going to be directly on the plane, right, of the xy plane, directly at the center, and then it's just going to be moved up in the z direction. So nothing too bad. So cool. So that means the only integral I'm going to have to do is this z integral. So we're going to have to find the z location, which again is going to be 1 over the total mass integral of the mass density integrated over the volume times z in this case. So cool. So let's redraw our picture. So now we know all we care about is the z direction. So instead of drawing this as a 3-dimension, I'm just going to draw it as a 2-dimension. But again, notice it is actually a 3-dimension. So I want to know, what is the location of my center of mass? So all I'm going to do in this case is I'm going to chop this thing up into a whole bunch of planar slices, right? So I'm going to chop this up basically into a disk. So if I'm looking at it in more of a 3-dimensional sense, so it's kind of doing this, I'm going to chop this up into a disk, right? It's going to look something like this, where this thing is going to have some radius. Let's call that the radius of r. And this is going to be at some height of z from the origin in this case. That's my z-axis. Is okay? So cool. So what do I know? So in this case, then, what can I do? I can say that my differential volume is going to be the same thing then as the area of this disk here. So this is going to be my area times then the thickness of this disk, or I'm going to say the thickness of this disk is some dz, which is some differential thickness to it. So as long as it's differential, that means that the area is constant on both sides. Okay. So cool. So next things next is we know this is our A. This is my radius of A. And then this guy here is going to be my radius. So A again is just the radius of the actual hemisphere. And then R here is going to be the radius of this area. It's doing okay. So cool. So first things first is we can rewrite R, because does R actually depend on Z, right? So let's say it this way. So I know the area of this disk here is just going to be pi r squared dz, right? So I'm integrating over Z, but is R here independent of Z?
No.
No, right? Because as I move upward, right? So let's say I cut this portion here, then this r distance here is less than the r distance here, which is then going to be less than the r distance if I chopped it here, right? So r is actually dependent on z. So first thing I'm going to have to do is I'm going to have to reparameterize then r in terms of z. So how would I do that? So I have an r squared, right? So I'm going to draw out my picture here. So this is my a, this is my z, and then this is my r. So how could I rewrite R in terms of A and Z in this case?
A squared minus Z squared.
Good job. So this is going to be my A squared minus Z squared. We're just using Pythagorean theorem, absolutely, which says that Z A squared, well, R squared plus Z squared is equal to A squared. So that's right. So Z squared then becomes A squared minus Z squared. So let's put that in here. So finally, my differential volume then is going to become pi times A squared minus Z squared dz. So this is my differential volume. And I have a cat that really wants to get in my bedroom. So she's meowing at the door and scratching the door, but it's okay. She can stay out there. Okay. Everyone's okay? Sounds perfect. So now we can put all this together. So finally, my z position of my center of mass is going to be 1 over my total mass integral of my z position times the mass density times my differential volume. So my mass density I know is a constant, so let's pull that out. So it's going to be my mass density divided by the mass integral of z times a squared minus z squared. And let me pull the pi out front too, because that's a constant, dz. Everybody's doing okay? What are my bounds of integration? So I'm integrating over the z direction. Mhm. Let me kind of back up a little bit here. So this is my z that I'm integrating over. So I'm integrating in this direction here. So what are my bounds of integration?
0 to a.
0 to a. Absolutely. So good. So we're going to integrate this guy from 0 to a. Perfect. So let's split this up into two different integrals. I'm going to have a pi rho over m. And then we're going to have a integral 0 to a squared. I'm going to pull that up front. So I'm going to have a dz or a z dz minus then the integral from 0 to a of z cubed dz. What's the integral of z dz?
B squared with
B
it.
squared over 2.
Good. Uh, z squared over 2. So that guy's going to become equal to a squared, z squared over 2. And what's the integral of z cubed dz?
B to the fourth divided by 4.
Good. So 1/4 z to the fourth, all evaluated from 0 to a. Right? So I've evaluated 0. Of course, everything is 0. So this guy's just going to become pi, or yeah, pi rho m. This term here is going to become an a to the fourth. This term is also going to become an a to the fourth. So let's pull out the a to the fourth. So I'm going to get an a to the fourth times 1/2 minus 1/4. What's 1/2 minus 1/4?
1/4.
1/4. Fantastic. So we're going to get a pi rho a to the fourth over 4m. Okay. So finally, what we also know is rho. So what we already did was 3. So what was that? 3m over 2 pi a cubed. So let's put that in to this expression here. And then let's simplify. And so let's do that. So finally, we get z then is equal to pi a to the fourth over m times 3m over 2 pi a cubed. And I forgot a factor of 4 somewhere. That's factor of 4. There we go. Good. So from here, of course, the pi's are going to cancel. This a to the fourth is going to become just an a because of the a cubed on the bottom. And the m's are going to cancel, so it doesn't depend on the total mass. So this thing then is just going to become what? 3/8 of a. Okay. So my z location of the center of mass is 3/8 a. My y position is 0. My x position is 0, which means the location of my total center of mass is then going to be simply 3/8 a in the z hat direction. So this is my center of mass position according to this coordinate system. Doing okay? Doing pretty well? Good. So let's do another one. So this time we're going to do exactly the same problem, except now we're going to do a hollow hemisphere instead of a solid hemisphere. So again, here's my hemisphere. Okay. So again, this thing is going to have some radius of a. But now in this case, this thing is going to be hollow. So basically, it's just a hemispherical shell. So meaning that all the mass is on the shell, nothing on the interior. Are we doing okay? So good. So let's revisit this one. So first things first, is the center mass going to be at the same location as that of the hemispherical or the solid hemisphere?
Not.
No, right? Because in this case, we have no mass contained on the inside, so that means it's going to be pushed upward, right? It's not going to be at exactly the same location, right? So good. So let's do this one. So basically, we're going to do this similar, but now what are we going to do? So in this case, we're going to say that what? Again, I'm going to chop this thing. We're going to use a coordinate system very similar to what we did before. So I'm going to call this my x direction, my y direction, and my z direction. So that again, my x center of mass will be equal to my y center mass, which is going to be equal to 0. So that, again, we're going to look at only our two-dimensional projection of this guy. So again, all we care about is that z direction. Just like before, I'm going to chop this thing up into a slice, right? Or again, let me draw more of what this thing is looking like. So basically what we're doing in this case then is we're cutting out a ring. So here is my ring that I am chopping out. So in this case, this is just a ring. But again, this guy's going to have some radius of r. And again, we have our area vector, or not our area vector, sorry, our radial vector in this case. So that's my radius. Now, in this case, since I'm cutting out a ring, what we're going to do then is we're actually going to use arc length in this case. So in this case, I'm going to chop this thing up so that it's going to cut out this little wedge here, and we're going to integrate over this portion here. So this is going to be my dl. And we're going to split that up into this, where this is going to be our d theta. It's okay with that? So cool. So let's talk about this. So in this case, what are we going to do here? So we're going to do our arc length integral, which basically means that what? So we're going to have that our differential length that we're going to integrate over is going to be 2 pi r dl, or let me do it this way. So this is going to be a 2 pi r a d theta. Now, what I'm doing here, this is actually my differential area, I should say, not my differential length. That's my differential area. So because this is a sphere, this is a two-dimensional object, right? So this is a 2D object, which means we're looking at an area symmetry in this case. It's okay with that. So my differential area in this case is simply going to be this guy. Okay, so this portion here comes from my arc length, and then this portion here then is just what? The circumference or the perimeter of the ring. Is okay? Good. Now, just like we did in the previous problem, we know r is going to be equal to the square root of a squared minus z squared. So let's plug that in. So my differential area then is going to be the same thing then as 2 pi a times the square root of a squared minus z squared d theta. It's okay? Now, last thing is I have two choices. In this case, we can notice that, again, going back to my picture, as this guy changes, right, to this location here, my angle then is going to change as well, right? So initially this is my angle, and here this is also my angle, which means that what? R is actually going to be a function of theta. So that means that what? Theta, though, simultaneously is a function of z. So basically we have a couple different choices here. We could turn this into a arc length integral by simply changing z into a function of theta and then do this as a theta, or we can change theta into a function of z and then do this as a z integral. Either one is fine. Now, the one that's probably going to be easier is to change this into a z integral, so let's go ahead and do that. So first of all, let's write theta as a function of z. So the easiest way to do that is we know that going back to my original picture, so if we can see my original picture here, so I'm going to kind of draw this here. So we know this is a, this is what? Z, and this is r. And then this is my angle of theta. So theta then, at least z, is going to be the same thing as what? A times sine of theta. Okay. So in this case, we can then write theta as then being equal to the arc or inverse sine of what? Z over A. It's okay with that? Joey looks like he's sleeping. It's early, I know. So in this case, all we're going to do then is what? So theta then is going to be the arc or inverse sine of, again, z over a. So from here, all we're going to do is take a derivative of both sides. So I have a d theta then is going to be equal then to the derivative of arc sine of z over a. As I draw my pen. So the derivative of arc sine, as it turns out, is actually going to be the same thing as dz divided by the square root of a squared minus z squared. Okay. So basically, all we're going to do is we're going to replace now this into here, right? Or more appropriately, this into here. So what happens then is that this and this are going to cancel, which means ultimately my differential area then is going to become equal to 2 pi a dz. So good. So now we can write our z. Our z then is going to be equal to 1 over the total mass. And then we're going to have the integral of the z location. Now, since we're doing area integral, this is going to be sigma, which is the surface mass density, if I knew how to speak, a times then dz. And just like last time, we're going to integrate this then from 0 to a. So a is a constant, z is a constant. So we're going to pull all those guys out. So I'm going to get a sigma over m integral of z dz from 0 to a. So you guys already told me the integral of z dz is 1/2 z squared. So I'm going to get a 1/2 a sigma over m z squared, which is then going to become an a squared. So it's going to be the same thing then as sigma a cubed over 2m. Okay? Last thing is, what's sigma? So we know sigma in this case then is going to be equal to the total mass divided by the total surface area. So this is my surface area. So what's the surface area of a sphere?
4/3 pi r cubed.
That's the volume. What's the surface area?
Oh, you're right.
So take the derivative of that with respect to r.
4 pi r squared.
4 pi r squared, and then we have half of that, right? Because we have a hemisphere. So that means my total
2
surface
pi
area
r.
is going to be the same thing as 2 pi a squared. So good. So let's plug that in. So I'm going to get an m a cubed over a. I have a 2, so it's going to become a 4 pi a squared, right? Oh, I forgot my 2 pi. I forgot my 2 pi. There should be a 2 pi here, and 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 a 2 pi here. I forgot my 2 pi. So my pi's are going to cancel. This a is going to become an a. This is going to give me my square. That's going to cancel out. And then what? Let's see, my sigma here. Did I put my sigma in? So that's a 4a squared. Good. So this 2 is going to cancel with this 2, make that a half. I need my m on the bottom, so my m's are going to cancel. So good. So ultimately, this guy's going to become equal to what? 1/2 of a. There we go. I knew how to do math. So, okay. So my center of mass of my hemisphere then is going to be directly at the center of the z direction. So this is going to be my center of mass in this case. So cool. So this says then that for my hemispherical shell, my center of mass location is going to be a over 2 in the z hat direction, which is slightly higher than that 3/8 that we had from the previous hemispherical or a solid hemisphere. There you go. That's what I'm looking for. That was okay. Not too bad. Not too bad. So cool. So, what do we got about 14 minutes? So, last thing I'll talk about then is in terms of the center of mass, what happens then is for objects which are moving, whether that is a collection of objects or a continuous object, then they're all going to move about the center of mass. So, the motion then, also the dynamics, are about the center of mass. So that means for an object which is moving, so let's say here's my object, which is moving with some sort of velocity v, the momentum then becomes the net momentum, which is then simply going to be equal then to the sum over all the individual momenta of this particular object, which is going to be the same thing then as what? The sum over the mass times the velocity of each one of those particles, which is going to be the same thing then as what? The total mass times the time rate of change of the center of mass position. If this thing is experiencing an acceleration, i.e. has a net force which is acting onto it, in this case, then the sum of the forces is simply then going to be equal to the total mass times then the center of mass acceleration. So for a continuous object, or a collection of objects, then the total acceleration will be that of the center of mass acceleration, which means the total force will be acting directly at the center of mass. And then for the momentum will be directly at the center of mass with the center of mass velocity. That's it. So cool. So now I'm going to put you guys to work because Joey looks too sleepy, so now he's going to work. So we're going to have in this case is I'm going to make you guys all determine the center of mass of an inverted cone. So let's say here's my inverted cone, where my inverted cone has a total radius, let's call that capital R, and it has a total height of capital H. And what I want you guys to do in this case then, again, is find the center of mass location for this guy using any coordinate system that you want to, but there's one obvious one that you probably want to use, but we're going to write it this way. So, I don't know. You guys want to work on it independently, or you want me to break it up into like groups or what do I call them? Breakout rooms. Put you about like 2 or 3 of you in a breakout room.
Before we proceed,
Yes.
what's the volume of a cone?
Oh, what's the volume of the cone? Good question. Let's see here. I have to remember. So it is. Good question. Okay, so what's the volume of the cone? I used to know this and I forgot. Okay, so volume. Let me look it up real quick and then I'll write it down. So volume of a cone. There it is. I know it has a height squared, a radius squared. Okay, so it is the volume of this cone is pi times the radius cubed times the height divided by 3. So this is the volume of the cone. So, okay, so let's do some breakout rooms then. That sounds like fun. So let me stop sharing. Let's see. I gotta remember how to do breakout rooms here. Where are we doing? I remember how to put you guys in breakout rooms.
No idea.
It's been a long time since I've done that. I got poll. Oh, there we go. Breakout rooms. There we go. How many rooms do we have? So we have 7 of you guys. So let's do 3 breakout rooms. Sounds good. Assign automatically.
I
Okay.
think there's only 6 of us.
Only 6 of you?
Maybe because there's one of you. And then there's
Or 7. So 1, 2, 3.
No, it's 7, I think.
Yeah.
I can't count. Well, up here.
There was 6, but then Christopher joined, so that brings us to 7.
Oh,
So-
okay.
Okay, so let's do 3 rooms. So that would put 2 in each room, except for one will have 3. So, okay, so I don't know. I'll give you guys like 7 minutes, and then I'll pull you out of the breakout rooms, and then we'll compare. Sounds good. All right, I'll see you in a bit. Open all rooms. Here we go. So join a room.
Squared, which is
How goes life?
it's going
Pretty
well.
good.
Yeah,
Good life.
Life.
good life.
There you go. Very nice. And everything on the problems going okay so far?
I
Yeah,
think so, hopefully.
we got the origin centered at the center, so then it's just x equals y equals 0
Good. And are you doing it the top or at the bottom?
at the top.
At the top.
Yes.
So, okay.
Yeah.
Sounds good.
Well, since it was an upside down cone, the top.
Okay, so at the point,
No.
No.
the flat
Yeah.
point. Okay, gotcha.
Mhm.
Okay. I got you. Cool. Okay. I'm gonna go
Yeah.
check on everybody else. I'll be back.
Sounds good.
So do we want like a ratio of the triangles? Because it's not going to follow exactly the cylindrical. It's
How are we doing so far?
So far,
You what?
so far we have, uh, sorry, we have
Uh,
kind of the drawing here
good.
of we took it as a like a triangle kind of a cone,
Yep.
and then we're using the that big R and big H are Z dependent
Yes. Good.
to figure out the equation for that.
Okay, cool. Yeah, you're just gonna use similar triangles. Yeah.
Okay.
Nice. Good.
Yeah.
Okay. I'm gonna go check on everybody else. I'll be back.
All right.
So, mhm.
Actually, no.
Good morning. How's everybody doing so far?
Great. Great.
Doesn't sound great, but that's okay.
No, no, it's just a little stuck. Just a little stuck.
Gotcha. Okay.
Because when we were comparing to the like, because it's not similar, but it's the same idea as the solid hemisphere, right? You
Yep.
find set up your coordinate system at the base so that you only have to find the z.
Yep.
Um, but when you set up like you want to set up a derivation with respect to z to find your z.
Yep.
In the solid hemisphere, we compared the a and the r, right?
Yep.
But how do you do this? Because both of them change now.
Correct. So easiest way to do this now is to use similar triangles. So what you can say in this case then is that the total height versus the radius for the entire thing must then be equal to the height z versus r, right?
So you
So
do ratios? Is what
yeah,
you're
just
saying?
a ratio. Exactly.
Okay.
Yeah, exactly.
Okay.
So yeah, so just the
So
idea
like,
of similar
so you
triangles.
take
So
you're saying you take a flat triangle instead of just a cone? You take the triangle
right,
and you
because if
figure out
you
the
set
cone?
your coordinate system so that way, for example, it lies directly on the center of the XY plane, then you could just picture it as a two-dimensional object instead of a three-dimensional object.
Yeah.
Yeah.
So
And
then
mhm.
pretty much the dr with respect to dh, kind of like the
Yeah, so
change
you're gonna
there.
have a little r over a little z is equal to big R over capital H.
Huh.
Yeah. So that way z then is going to be equal to big R over, or sorry, R is going to be equal to big R over H times Z. So it's going to be a relationship between the two.
All right. I think I understand your idea, but I'll try to.
Okay.
Thank
Sounds good. Sounds good.
you.
You're welcome. All right. Check on everybody else.
Big roll.
Everybody still doing okay?
Yes, we think.
Okay.
Um,
You got a lot of that. So yeah. Mhm.
equals 1 over m times rho z pi r squared dz, where r squared is equal to a squared minus z squared. Does it sound like we're on the right track, Dr. Greenwood?
Sorry, I was zoning out there for a second. Sorry, can you say that again?
So we're kind of doing it like how we did it with the discs.
Yes.
We're breaking it up in like smaller, pretty much smaller cones.
Yes.
And
Yeah.
then we have like the r squared is equal to a squared minus z squared.
Oh, no, you don't have to do it that way. Just use similar triangles. So here, I'll kind of show you what I mean.
Okay.
Do. Hmm. Sorry, it's a process to share here. There we go. Okay. So basically, since it's kind of two-dimensional, right? Because you said you're going to put all that stuff there. So you're just going to draw this guy here. Same as before, you're just going to cut out this wedge. And then this is your z-axis. So this would be r, this would be z. And then you know this is capital R and this is capital H. So similar triangles tells you that what? Oh, R over Z must be equal to capital R over H. So that way little r is equal to capital R over H times Z. Can you see anything I'm doing?
I
No,
can't.
No.
but vaguely what you said does make sense.
Okay. Here, let me, what did I do here? All right. Hang on. Let me unshare. Stop mirroring. There we go. Okay. Here. Let me stop my share. Well, we're basically out of time, so let me pull everybody out of the rooms, and then I'll kind of talk about that real quick. Okay. So all right, welcome back, everyone. Hopefully, most of you. So good. So let me share real quick. I'll talk about. Let me know if it doesn't work this time, because apparently it wasn't working last time. All right, so. Okay. Can everybody see my share this time?
I cannot.
Not. Okay. And let's see here. Okay. How about we talk about this on Friday since it's not.
And
Okay.
sorry, I have a
So,
class.
anyways, yeah, so keep working on it, but basically all you're going to do is set it up as similar triangles, right? So draw it as a two-dimensional shape, and then to get the relationship between R and Z, because R will be Z dependent, just use the total cone. So that way you know the total height is H versus the total radius is R, and set up your little triangle so that way the total height in your case is little Z versus R. Okay. And then that'll give you a relationship between R and Z, and then you can just do it that way.
Okay.
Because for some reason, this thing is not sharing properly. So, but that's okay. So,
Thank you.
you're welcome. All right.
Yeah.
Hopefully I'll be back on campus on Friday, but it depends on my kid's school. So we'll see what happens. All
Fair
right.
enough.
Yep.
So
Bye.
have a good one, everyone, and I will see you hopefully soon.
You too, Dr. Greenwood.
All right. Have a good day, guys. And
Yep.
gals. Sorry. All right. Bye.